recording. Okay, so now I've got it on. All right, so now the recording is on, so we didn't lose too much there. I want to look at a couple of the problems from the algebra view. I was kind of looking at the ones that it looked like people were having the most attempts on. And so just to, but if you have any questions, then go ahead and you can ask me questions as well if you have any questions about this. So I'm just going to hit just a couple of them as highlights. Let me see if I can move some of my boxes here out of the way, and so I can scroll through this. Let's see. Let me see what the first one is that I marked to myself. But now these may not be your questions again. So if you have questions, then you can go ahead and ask me separately from these problems. All right. So the first one that I wrote down that some people were apparently having questions about is just a very basic algebra question number 3, right? Okay. So it just says you want to simplify this expression. That's not really the instruction there, but that's how I would give the instruction for this problem number 3 is just to simplify that expression. So what that means is to carry out by hand all of the operations in that expression, right? Okay, so so just as a reminder of how to do that in this expression, so we don't have to go through the steps, but just as a reminder in this problem, to simplify this expression, you're going to go ahead and do the multiplications here, right? So wherever you see parentheses, right, that's going to imply usually some sort of multiplication, correct? So here you would take the 4 and multiply it by the 2 minus 3t, right? So be sure you distribute it, right? So you're going to multiply the 4 times the 2 and the 4 times the minus 3t as well. And then same thing here in this second term, you're going to take the t squared and multiply it by the t and the minus 1, right? So you distribute that t squared, right? So you would get t squared times t, that's going to be t cubed, and then t squared times minus 1 is going to be minus t squared, right? And then same thing in the third term here, you're going to distribute as well. But here you're distributing this minus 1 coefficient. This is an implied minus 1 coefficient, or you can think of it as just distributing the minus sign, which is going to change the signs inside the parentheses, right? So you would have minus t to the 4th and then plus 3, right? Minus 3 is going to be plus 3. So that's how you eliminate the parentheses from the expression, is just by carrying out these multiplications, right? And then add like terms together. So if you have any like terms, you're going to combine those, right? So you do the addition and subtraction to combine like terms. And of course, you're still going to end up with some variables in the expression when you're finished, right? You can't do anything with the t, but just combine the like terms, and then that would be fully simplified by hand. So you just write your final answer there, you see, okay? So again, all we're doing here is, in some of these problems, is just carrying out what arithmetic we can by hand, and then that's it, all right? Fully carrying out the arithmetic that we can by hand, and then just typing in, the expression. So we also had problems with number 4, which is really the same sort of problem, right? Okay, so in that problem, it's x plus 2 times x squared plus 6x plus 5. So again, the instruction says simplify, right? That means you want to carry out by hand, right, all of the operations that you can carry out, okay? But you can't carry out all the operations by hand because some of those operations will involve variables, right? Well, in particular, the variable x. You won't be able to completely simplify operations that involve the variable x because you don't have a value for the variable x. But you do what you can by hand, right? And then when you're finished, whatever you get is going to be the answer that you'll enter, right? But now what's complicated about this one is it's just a little bit more difficult expression to simplify. Okay, so let me see if I can go through just a few steps of this one, but we don't have to go through all of the steps. So let me find some blank paper here. I didn't write this down, unfortunately, beforehand, so I'm going to write it down now. So the problem was, let's see, the problem there is x plus 2, right, times x squared. My version of the problem, your version might be slightly different, but x squared plus 6x plus 5, right? Okay, so there it is. And right, and so we're going to carry out what operations we can. So the first thing you'll do, of course, is this multiplication, right? The multiplication that's implied by these two sets of parentheses. Now, I know what messed up some people here is the distributing terms between these two sets of parentheses, right? Because to carry out the multiplication, you have to multiply every term in the first set of parentheses by every term in the second set of parentheses. So you have to be a little bit patient here, right? So you just take this one step at a time. So start with the x, right? And multiply the x through the second set of parentheses, right? So you have x times x squared is x cubed. X times 6x is 6x squared. X times 5 is 5x. And then repeat that same operation, right, for the 2. So 2 times x squared is 2x squared, right? 2 times 6x is 12x. And then 2 times 5 is 10. See, now you're done with the multiplication. You've eliminated the parentheses. You still have multiplications in your expression, right? Because, for instance, you have 6 times x squared, but you can't simplify 6 times x squared, right? Because you don't have the value for x. So essentially, you're done with the essentially, you're done there with the multiplications. Now you're going to do additions and subtractions. So you're going to add like terms together. Let's see, what are like terms here? Well, this first term is an x cubed term, but you don't have any more x cubed terms, right? So nothing to do with x cubed. But you do have 2x squared terms, right? So you can add those together, and that gives you 8x squared. 6x squared plus 2x squared is 8x squared. 5x plus 12x, those are like terms. So you get 17x there. And then finally, at the end, you have this constant term 10. It's constant because it doesn't have a variable in it, right? But that's just by itself. There's no other constant that you can add to the 10. So there's your final final answer there, right? Okay, and that's what you would enter there as the that's what you would enter as the answer. Any questions about that? Did that trip anybody up, or did it just take a couple of attempts, or did you just make some a slight error on that? Because we had a few that were missing it. Now there were other people that missed it, so you don't have to be shy about don't have to be shy there about speaking up. Okay, let me see if I can hang on a minute here. I'm going to mute everybody temporarily, but you can unmute yourself if you need to. You can unmute yourself if you need to talk. All right, or you can chat. I've got the chat screen on, so I think hopefully I'll be able to see that. So if you want to ask me a question, just unmute yourself. All right. Now, this one is also a simplification problem, but I know I had questions about this one. So this one probably tripped up a few people just because you're, I don't know, for some reason, students are always freaked out when they see fractional exponents. All right. So, and these are kind of unusual fractional exponents in this problem. These are not fractional exponents you're going to see frequently. All right. But this is just an example problem. So we have y to the 1/6 power times y to the 11/6 power plus y to the 23 over 6 power. In a minute, we're going to remind ourselves what it means to take a number and raise it to the 1/6 power, or to take a number and raise it to the 11/6 power, much less take it and raise it to the 23 over 6 power. But you really don't need to know that in order to simplify this expression. Okay, let me show you why. So you don't need to get hung up here on, gee, what does it mean to raise y to the 11 over 6 power, right? I mean, what sort of strange thing is that, right? You can still simplify this without knowing really anything about fractional exponents. So we have y to the 1/6 times y to the 11/6 plus y to the 23/6 power. That's hard to say. All right. But again, we're simplifying, right? So that means we're carrying out the operations that we can by hand. So the key operation here is going to be this multiplication, again, implied by the parentheses. So you just distribute. You take y to the 1/6 and you multiply it by both terms inside the parentheses, right? So you have y to the 1/6 times y to the 11/6, right? And then plus y to the 1/6 times y to the 23 over 6. And the only thing you have to remember here to finish off the simplification is when you're multiplying powers that have the same base, these are powers of y, right? You have y raised to a power, you have y raised to a power. So when you're multiplying powers that have the same base, you can do that just by adding the exponents. So y to the 1/6 times y to the 11/6 is really y to the 1/6 plus 11/6. So you can add the exponents together. But how much is 1/6 plus 11/6? That's 12/6, right? But 12/6 reduces nicely because 6 goes into 12 twice, right? So you really have here y squared. See how nicely that works out? So y to the 1/6 times y to the 11/6. That seems like a really complicated expression, but it's not. It's just y squared. And same thing here, y to the 1/6 times y to the 23/6 is really y to the 24 over 6. But that's a convenient fraction, 24 over 6, because 6 goes into 24 4 times, doesn't it? So y to the 24 over 6 is just y to the 4th power. And there's your result. It's just y squared plus y to the 4th. So that's it, okay? You can't simplify that any further by hand. You can't carry out any more arithmetic in this expression by hand. So there's your there's your answer. So I know that sometimes confuses students because, again, they get hung up on the fractional exponents. Let me show you that again, because we're going to be working with fractional exponents a lot in the class. That turns out to be really crucial in calculus. So it's kind of important that we have kind of a good grasp of fractional exponents. All right, and remember, what we use fractional exponents for is to rewrite radical expressions. So that's what's happening here in problem number 17. All right, they have here a radical expression. All right, 1 over the 4th root of x to the 5th power. See, that expression has a radical in it, a 4th root in it, right? Okay, and they want you to rewrite that expression using exponents. And we have to do this sort of operation a lot in calculus. We have to take expressions that have radicals in them, like square roots or cube roots, or in this case, 4th roots. We don't see 4th roots that often, right? But sometimes, more likely a square root or a cube root. And we want to now take that and rewrite it as an expression with an exponent, not with a radical. Okay, and you'll soon understand why that's the case in calculus, because many of our rules that we learn in calculus to help us carry out calculus operations, they are expressed in terms of exponents, not in terms of radicals. So if we have an expression with a radical in it, we like to convert it to an expression with an exponent so that we can apply our calculus rules to that expression. All right, so let me show you how to do this here. As a reminder, again, I know you've done this lots of times, but students forget this sometimes because, you know, it's not something you do every day. So let me rewrite this expression. This is 1 over the fourth root of x to the 5th power. All right, so how do I rewrite that without the fourth root using an exponent? Okay, well, here is the trick. So let me show you the rule if you don't remember it. So if you have an expression that looks like this, okay, where you have some root, okay, of some base raised to a exponent, right? Some power, right? So you have some root of a power, x to the m is a power, right? That's a power of x. Then you can rewrite that in the following way. This is the same as x to the m over n. So see, you can rewrite radicals as fractional exponents. All right, you can rewrite radicals as fractional exponents. The index of the radical, the type of the radical becomes the denominator of the exponent, and this power under the radical, this m exponent here, it stays as an exponent, but in the numerator of this fractional exponent. All right, so the nth root of x to the m power is the same as x to the m over n. There's one little caveat to this, though, I've got to mention. The m over n, that fraction has to be in lowest terms. So it's got to be a reduced fraction. So if this were like 4 over 6, this rule wouldn't apply because 4 over 6 reduces to 2/3. So this equation works when this fraction is fully reduced. All right, well, let's see if we can apply that now to this. Let's see if we can apply this idea to this expression. So notice in the denominator of this fraction, you have the fourth root of x to the 5th power. So what is my rule here tell me? I can rewrite that as x to the what fractional exponent? The 4 becomes the denominator of the fraction. That looks really bad the way I was going to write that. Let me erase that. So the 4 becomes the denominator of a fractional exponent here, and the 5 stays as the top of that, the numerator of that fractional exponent. So you can't read that very well, but the fourth root of x to the 5th power is the same as 1 over, well, the 1 was already there, right? 1 over x to the 5/4 power, okay? So fourth root of x to the 5th is the same as writing x to the 5/4 power. Now, there's one other simplification we can do here because this is a reciprocal. So you have this x to the 5/4 power in the denominator. The way you can get that out of the denominator is change the sign of the exponent. So 1 over x to the 5/4 power is the same as x to the minus 5/4 power. But you don't have the power in the denominator. See, you can pull that out of the denominator by giving it a negative exponent. So your final answer here is x to the minus 5/4 power. Remember, when you have negative exponents, that means reciprocal. So negative exponent means reciprocal. Fractional exponent means some type of radical. So the right answer for this one was x to the minus 5/4 power. Are there any questions about that? Is that all? Was that all easy? Did y'all figure all that out? One more here, kind of similar, I think, is number 21. Oh, no, this is different. All right. Okay. So it also looked like this problem number 21 was causing y'all to have multiple attempts. And this is solving a quadratic equation. I think we've solved a couple of quadratic equations in class already. in the notes, but maybe that still was a question mark for you guys. So let's look at how we would start solving this one. I won't go through all the steps of the solution though, because once we get to a particular point, I think you'll know what to do. All right, so let me write this one down. So again, the version of this problem in your homework might be slightly different, but it's going to be a similar problem. So it might have slightly different numbers in it, slightly different coefficients in the problem, but it'll be still solving a quadratic equation. By the way, what makes this a quadratic equation? Why am I using quadratic? Can someone answer that for me? So when I look at this equation, why am I calling that quadratic? Kind of a college level word there, quadratic. Why am I calling that quadratic?
Because the squared variable.
That's right, because the x is squared. Perfect, right? Okay, so and that's correct. By the way, Lance, if the x were not squared, right? So if you just had x to the first power, like the 9x, right? Then what sort of equation would that be, Lance?
Linear.
Linear, right? You would call that linear, right? Okay. But this is not linear. This is quadratic, and quadratic a little bit more complicated than linear. So when students are beginning algebra, they usually you start with solving linear equations. For some students, they never, unfortunately, master solving linear equations. Okay. So those students change majors. But then you move on in your second algebra to quadratic equations, right? Okay, and then eventually you get to a much higher powers of x, right? And those equations become much more difficult to solve. All right, so but quadratic equations are pretty straightforward to solve. They've been solved since humans have known how to solve quadratic equations since antiquity. That means before recorded history. So humans have been solving quadratic equations for a long, long time. The reason we know that people have been solving these since antiquity is when the very earliest writing shows up in human civilization, which typically shows up in the Babylonian culture. Okay, then. In those very earliest writings, there's already indications of people solving quadratic equations. So that's been going on for a long time. All right. So how are we going to solve this one? Well, the two typical techniques for solving quadratic equations are either factoring. So I think we practiced that a couple of times already in the notes, factoring. But also, if you cannot factor to solve the quadratic equation, what is your second option? Can someone tell me that? So what's another possibility for solving quadratic equations if you're not able to factor?
Common dividers, like.
Yeah, Daniel, go ahead. What?
Common dividers, like we can choose a number, you can divide all the numbers.
Well, no, that might be part of a process, okay? But can you think of a name for a larger process that might involve what you're describing that we use for solving quadratic equations if you cannot factor? So do you recall, Daniel, if you end up with a quadratic equation and you cannot factor to solve it, what do you have to resort to solve that equation?
Using a formula.
Using a formula, that's right. How do you say your name? Is it Jocelyn or?
Yeah, it's like Jocelyn.
Jocelyn, okay. Yeah, Jocelyn. Daniel, do you remember that? So you use a formula, and the formula has a famous name. Remember the name for the formula?
I don't, but I remember it.
Well, the formula is also called the quadratic formula, okay, right? So because it's used to solve quadratic equations. All right, so you can solve any quadratic equation because you can either factor or you can use the quadratic formula. So quadratic equations, we always know that we're going to be able to find a solution to quadratic equations. But in both of those instances, usually it's easiest either to factor or to use the quadratic formula if you don't have any fractional coefficients. It's not essential, but usually it's easier. So what I would like to do is get rid of this -1/2. I do not want a -1/2 here. And I'd like to have just all integers, all whole number coefficients here. So the way you can do that is just strategically multiplying both sides of the equation by something. What can you multiply both sides of this equation by to get rid of that 1/2?
2.
I heard someone whisper it there. What?
2.
2. Yeah, sure. Right. Okay. So I'm just going to multiply both sides. Don't forget to do it on both sides. I'm going to multiply both sides by 2. Well, of course, 2 times 0 is just 0. So no effect on the right-hand side, which is good because we want the right-hand side to be 0. But on the left-hand side, we get 4x squared plus 18x minus 1. And now this is where we either try to factor, okay, or, oops, this is 18x, all right? So we either factor or we try to use the quadratic formula. I don't see that factoring here is going to be very useful, right? Okay, so so let's try applying the quadratic formula, and we'll just get started with this, but we won't go through all the steps. But you remember the quadratic formula? It's minus b plus or minus, so you might have two solutions to your quadratic equation, b squared minus 4ac over 2a, right? And remember the a, the b, and the c in the formula, of course the x is the unknown in the formula, right? But the a, b, and c in the formula are the coefficients for your equation, right? Make sure you have the equation set to 0. So when we start filling this in, we have minus 18, right, plus or minus, because b is 18, right? Oops, I forgot to mention that. This is the a, this is the b, and this is the c, right? So we have minus b, that's minus 18, plus or minus the square root of, we're going to get big numbers here, 18 squared, b squared, right? Minus 4 times a is 4, and what is c? Be careful here, what?
-1.
Minus 1, right? Yeah, not a 1, but minus 1. All over, forgot to write 2a here, all over 2 times 4, which is the a, right? So I get minus 18 plus or minus square root of, wow, guys, what's 18 squared? Is that 324? Think so. Okay, so 324, what's the second term going to be? Well, minus 4 times 4 is minus 16, but minus 16 times positive 1 is plus 16. So make sure you write plus 16 down there, all over 8. So we get minus 18 plus or minus the square root of 340 over 8. There are your two solutions to your quadratic equation. Minus 18 plus the square root of 340 over 8, whatever that number happens to be, okay? And then minus 18 minus the square root of 340 over 8. Now, you might be able to simplify this a little bit by hand. Again, what does simplify mean?
Combine like terms and like reduce it down as much as you can.
Yeah, so combine like terms and reduce it. That's all part of the process of carrying out as much of the arithmetic in this expression as you can, okay? So you're going to simplify means I'm going to do as much of this arithmetic by hand as I can. You're not going to be able to do all the arithmetic, though, in this expression by hand because 340 is not a perfect square. So, so you cannot completely simplify square root of 340. Okay, it just doesn't. It's just not going to completely simplify. Okay, but you can simplify it a little bit. Let's see if we can do that. So we have minus 18 plus or minus. The trick to simplifying square root of 340 by hand, so not going to use a calculator, okay? Not going to try to get an estimate for square root of 340, not yet anyway, all right? The way you can do this is, since I'm taking square root, let's try to write 340, let's try to write 340 as a perfect square times some other number. So, wow, what is 340? Let's try breaking that down. So 340 is, isn't that 4 times 10? Is that right? Can y'all see that? Yes, no?
Yes.
Yes, right. Okay. And let's see, 34 is, that's 2 times 17. And then 10 is 2 times 5. Well, look, here you have 2 times 2. That is a perfect square. So you have 2 squared times 17 times 5. 17 and 5 are both prime numbers, though, so you cannot break them down any further. But you can write the 2 times 2 as 2 squared. And what's the square root of 2 squared? That is 2. So you can extract from underneath this square root, you can extract a 2. See, so you can simplify that a little bit by hand. The square root of 2 squared is 2. Now you're left with 17 times 5. Wow, what's 17 times 5? Well, just it's 85, right? Okay, so let's keep going there. Still just simplifying this by hand. Now, notice from the numerator, you can factor out, what number can you factor out from the 18 and from this radical? What divides into both of these terms? I think you can factor out a 2, correct? So when you factor 2 from 18, that leaves you with minus 9, and then plus or minus the square root of 85, right? You factor this 2 out, all over 8. And the reason I factored that 2 out is now I can divide that with the 8. So I end up with, here's the final answer, simplified by hand. Minus 9 plus or minus the square root of 85 over 4. 2 goes into 8 4 times. So minus 9 plus the square root of 85 over 4, that's one of your solutions. Minus 9 minus the square root of 85 over 4. And now, since you've simplified it completely by hand, now, if you want to, you can use your calculator to get a decimal estimate for square root of 85. And then you can get a decimal estimate for what these two solutions are, okay? Because it's really hard to know what minus 9 plus the square root of 85 over 4 is approximately, right? Or what minus 9 minus the square root of 85 over 4 is approximately. But with a calculator, you can get a decimal approximation for these two solutions that give you an idea of, sort of the size of these two solutions. Well, that's kind of messy, right? Okay. Remember, we really had the two solutions here, but all of this was just trying to simplify by hand the two solutions, okay? All right, so if you were still working on that problem number 21, then maybe you can use this as a guide to help you finish that one. Shoot, it's logged me out here. So All right, so well, I'm not going to go back to that problem now. All right, so those are the ones that I saw kind of in the those are the ones that I kind of saw in the homework that people were asking questions about. Do y'all have any other questions that y'all want to ask about those homeworks in particular? So, I mean, we went through that pretty thoroughly. I usually won't go through the homework that carefully, but I did want to look at just those problems since I noticed them as maybe the ones that people were having, issues with. You can always go to Madison's SI session, and I'm sure she'll be able to or willing to answer more questions about those. Madison, did you figure out when your Wednesday session is going to be?
Oh, so I actually had to switch my Wednesday session to Thursday. So
Okay.
my sessions are going to be, for this class is going to be from 12 to 1 on Monday, and then 9 to 10 on Thursday.
Oh, 9 to 10 on Thursday. Okay, so 12 to 1 on, what is it, Monday?
Mm-hmm.
Yeah, and then 9 to 10 on Thursday. All right, okay. Well, so you won't get a chance to see Madison again before this homework is due, but before this homework comes up, right? There will still be other sessions. All right, so at least the Monday session, correct? Before this next homework is due. Okay, all right. So now let me go back to Zoom here, and if I can find my way back, and let's. I wanted to look at just a little bit of a review of things that we were talking about last time. So let's look at a couple of polls here. So remember, one of the things we discussed last time was we were talking about linear relations, and important aspect of linear relations is slope, right? So so I've got a little poll question for you on just what is the interpretation of slope? Do you remember, for slope of a line, what does slope of a line mean? Okay, so what do y'all think there? For this one. So remember, just you don't have to look back through your notes or anything, just off the top of your head, right? Can you remember, just what do you recall from last time as as kind of the meaning or the interpretation of slope?
I put all of the above.
Okay, all right. So several of you put all of the above, Mohammed. We'll talk about that in just a second. All right.
Oh, okay.
So, all right. So I've got several of you have voted. Just if you haven't voted yet, just try to vote. Okay. If you can, if you have a mechanism for doing that, right? Just vote quickly, right? Again, just try to recall your first impression there, right? Okay. You don't get grade on this, right? We're just kind of using this as a discussion point, right? To remind ourselves of slope. So vote for something. Got a few more of you there that need to vote there. Just try to remember something. Aha, so I think I've got some people who are playing hooky. So I may catch up with y'all in just a minute. All right, so if you didn't vote. All right, so I'm going to end the polling here, and and then I'll show the results, and we'll can y'all see those now, what people voted? So like can y'all see that? Yeah. Over half the people voted for the last one, right? And that actually is a very reasonable response, because slope does give you information about all of these first three things. Okay, slope does give you information about the rate at which a line is increasing or decreasing. All right. And that's what really makes it important. That's what really makes lines important to us in calculus, because again, we're going to be interested in how curves are increasing and decreasing, how curves are changing, right? As we move from left to right, how the y value is changing as x changes. Okay, so it's reasonable to believe that the right answer here is number 1. So a lot of people put all of the above, and that includes number 1. And actually, a lot of people answered number 1 here is the right answer. Some people put, oh no people put the orientation of a line in the plane, but slope does give you information about how a line is oriented, see, increasing or decreasing. So whether it's going up or down, right, from left to right in the plane, slope does give you information about that. Okay, but the actual correct answer is the third one. All right, so this is the best answer. The slope is the change in y. This is the interpretation we're going to give. The change in y when x increases by exactly 1 unit. All right, so we that's our really kind of precise interpretation of slope. All right, but that's not to say that number 1 is not doesn't have some truth to it, right? Or even that number 2 has some truth to it. But this is the actual technical interpretation that we want to give to slope. Okay, so it's the change in y when x increases by exactly 1 unit. All right. Okay, that's going to come up again in just a moment here. So, whoops. Let me try our next poll here. All right, so this is another thing that we talked about right at the end of class last time, and that is a tangent line. Okay, so a tangent line is a particular type of line that's of interest to us. So do you recall from last time, what is the tangent line to a curve that may not be a line at a given point? Okay, so what makes a line a tangent line to a curve at a given point? That last one is none of these. I can't see it on my screen too well, but the last option there is none of these. So we really did tangent lines right at the end of class last time. So can you kind of remember what that was? So again, you don't have to look through your notes too carefully, right? Just is anything that you recall that I said last time about tangent lines, that any of that stick with you?
Hey, no.
That's and kind of indicated in one of these responses. Okay, so most people have voted there, so I'm going to end the polling and show the results there. All right, so we had all over the board here again, okay, with our answers, and that's because all of the answers there are kind of correct, all right, but one of them is the most correct. So a lot of people answered there, half the class answered the line that intersects the curve at that given point, okay? And that's sort of true because typically the tangent line will touch the curve at the point, all right? So when you have a curve and you choose a particular point on that curve and you think about the tangent line at that point, usually the tangent line will, in fact, always the tangent line will touch the curve at that point, okay? So it will intersect the curve at that point, okay? But lots of lines will intersect the curve at that point, okay? The tangent line has kind of other special properties that make it a tangent line. So answer 1 there is, although it's true, is not quite correct. All right. Answer 2 is also kind of partially correct. All right. Because answer 2 and 3 kind of say the same thing. All right. 2 says the line that parallels the curve at the given point. Right. And then 3 says the line that duplicates the curve at the given point. But the actual better answer is 3. Okay. So a tangent line duplicates a curve at a given point. So remember, if you have a curve and you choose a point on that curve and you sort of zoom in on that curve at that point, so you sort of magnify the curve at that point. If you magnify the curve large enough, eventually the curve is going to look like a straight line. Okay, you won't see the curvature in the curve any longer. If you blow up or magnify that curve enough, the curve will look like just like a straight line. Your eye will not be able to detect any curvature in that curve if you zoom in close enough to the given point. So if you zoom in close enough to the point, you're going to see a straight line. You're not going to see a curve. You're going to think the line, you're going to think the curve is a straight line. And that line that you're looking at, that is the tangent line. Okay. So, so we say the tangent line duplicates the curve at a point. Okay. That's kind of the same as parallels the curve at the point, but I like to use that language of duplicates a little bit better. So I would say that 3 is the better answer in that case. All right. Ooh, so if you answered one of these, well, actually any of these, okay, you remembered something from last time. So so that's great. All right. All right. Let's get rid of the polling now. So there's our little quick review from last time. All right, now I'm going to switch back to before we take a break here, I'm going to switch back to the notes, and I want to look at one problem before I'm going to let y'all do a problem. So I'm going to scroll up here just a little bit into my notes. Let me see if I can get my windows here arranged properly so that I can write and so that y'all can see this. All right, so we've looked at this example. So I'm looking at problem number 3 here. Let me change the share so that we're just looking at the notes here. So we switch to this share. All right, so are y'all seeing the notes now? Are y'all looking at just the notes here? Problem number 3, is that showing right?
Yes.
Yeah, okay. All right, so because I cannot tell easily what y'all are actually looking at. All right, so remember that this was one of the very first examples we did last week, and this was a linear relation, right? Here's the formula for the linear relation that related life expectancy for female high school dropouts, right? Remember, to elapsed years after 1990. Here's the you don't see the whole graph, or well, I don't know what you're seeing, but you may not see the whole graph there. Remember, this is a linear relation, so when you graph this equation, you get this straight line. It looks like this. So there's a really quick graph there. And remember, what's kind of disturbing about this graph is the the line is going downhill from left to right, correct? Okay. Which meant that I'm going to mute everyone again there. So, which meant that that life expectancy, right, had been for female high school dropouts has been decreasing, which is not a happy fact, okay? But that's the case there. All right. All right. So so this is a linear relation, right? So it has all of the features that that linear relations do, okay? And so let's answer some questions, quick questions there about this particular linear relation. The first thing it asks for is, what is the slope and the y-intercept of this line, right? Okay, so to answer that question, you have to take your linear relation, and remember, you have to put it into slope-intercept form. So that means you have to solve the equation for y, all right? You have to solve the equation for y, and so I lost my chat there, but okay, so you have to solve the equation for y, and so that means you just in this case just take the other terms other than y, right, and move them to the other side of the equation. So I get y is equal to minus 0.22x plus 78. So there's the equation written in slope-intercept form, solved for y, correct? And simplified. The right-hand side is simplified. And when you've got the equation solved for y and the left-hand side is simplified, then it's very easy to write down what the slope and the y-intercept are. What's the slope here? So what is the slope for this particular line, guys? Remember, we usually denote the slope by m. So what is the slope there?
Negative 0.22.
What now? Yeah, minus 0.22. Exactly right. Okay. So there's the slope, minus 0.22. That's the coefficient of the x. And what's the y-intercept? We usually denote that by b when we're working with straight lines. So what's the y-intercept here? You can see it there on the graph, but what is that value there where that line crosses the y-axis? What is that exactly? You can't read it off the graph very well, but we can see it from the equation. It's going to be what?
78.
Did someone chat me there? What?
78.
78, exactly. Perfect. Yeah. Okay. So the y-intercept there is 78, right? So that number right there that we can't see very well, that is 78. Okay. All right. So that was easy, right? Very easy question about lines. All we have to do is take our linear relation, right, and write it in slope-intercept form. Here's the hard question. Okay. I want to explain the meaning of these values in context. In other words, I want to interpret the meaning of the slope in context, and I want to interpret the meaning of the y-intercept in context. Well, let's start with the y-intercept first, because that is simple. Okay, what is the y-intercept telling me? Well, that, of course, is where the graph crosses the y-axis. But that answer is not in context, okay? In the context of the problem, what is the y-intercept telling me? I mean, it's true in general that y-intercepts are where graphs cross the y-axis. That's always true. But in the context of this problem, what does that number 78 mean to me? All right. Well, that's pretty easy to understand as well. See, 78 means when x is 0, right? When x is 0, y is 78. So what does x in this problem mean? What is the variable x telling me? That's elapsed years after 1990. So when x is 0, what year are we dealing with, are referring to?
1990.
1990, that's right. Okay,
1990.
so so the y-intercept is telling us something about 1990, and so what was happening in 1990? So that's the 78. That's the y value. What's the y value again? You can just read it off the screen there. That's what? What's y?
78.
Right. Okay. So, Colin, but the y is 78. But what is y measuring?
Life expectancy.
Life expectancy. So, Colin, can you put all that together for me? So, something about 1990, something about life expectancy. How would you write that down in a nice sentence? If you were in your English class, how would you write?
In 1990, the life expectancy of whatever that is would be 78.
Yeah, that's right. So in 1990, right? Okay, life expectancy of, it was female high school dropouts, right? life expectancy is 78. Okay, if I can spell expectancy. So life expectancy is, or was, I guess, 78. Okay. All right. So see, that's too easy, right? Okay. But that's what I mean by interpreting a value in the context of the problem. Now, the harder one is slope. Okay, and it's not that understanding what the slope is telling you is difficult necessarily, but trying to get it written down in a way that I'm going to give you full credit for. Okay, that's what might be a little bit more difficult. Okay, all right. So Colin, help me here again. All right. So what was the basic interpretation of slope? Remember from our poll question just a moment ago?
I remember about the slope for 1 unit.
That's right. The slope was the change in y when x increases by 1 unit. Okay, so we know in this problem, let's see, y is changing by, well, what is my slope value? What is the slope value here?
Oh,
Colin?
it's changing by negative 0.22.
Yeah, so minus 0.22 when what's happening here?
The year changes by 1.
Yeah, you're even ahead of me here, right? I'm taking it very
Okay.
slowly. So I'm going to say when x, I'm going to just call it x for a moment here. When x increases by 1. Okay, that's the basic interpretation of slope. All right, but now look, we're all adults here, right? So we can explain this a little bit better than this sentence. Y is changing by minus 0.22 and x increases by 1. Okay, I can certainly say this better by actually saying what y is and what x is. So Colin, that's what you were already doing for me because you were already anticipating how we should really be explaining this, right? So what is y? You just said it before.
Life expectancy.
Yeah, so life expectancy is changing, but this is negative, so we don't have to say changing by a negative amount. If you're changing by a negative amount, what's happening?
Decreasing.
Yeah, decreasing. Yeah, you don't say change by a negative amount, right? You would say decreasing. So life expectancy is decreasing by 0.22. 0.22 what? Is that feet or hours or? How do we measure life expectancy? What?
Years.
Yeah, by 0.22 years, right? Now, when x increases by 1, so how can we make that a little bit smoother, Colin, than saying just when x increases by 1? After all, what is x?
So we would say per year.
Yeah, perfect. Yeah, you said it great there. Per year. Yeah, when x increases by 1, x is calendar years, right? So you could say when the calendar year increases by 1, who says that though? You would say per year, right? Okay, so life expectancy of these female high school dropouts is decreasing by 0.22 years per year, all right? So each year that goes by, right, the life expectancy was falling by 0.22. We'd like to change that trend, but that's the trend that's currently in effect, right? Okay, now, all right, so there's a kind of a little quick there explanation of how you interpret slope. All right, now I'm going to give y'all a problem to work on here. All right, but we're going to take it one step at a time. Okay, we're going to take it one step at a time. Notice this is completely stated, so I don't have a formula. All right, but so in number 5, it says the average annual earnings Y for adult men. All right, so we're going to look at adult here men instead of female high school dropouts. that increases at a steady rate as their high school GPA increases. So an adult male whose high school GPA was 1, that's kind of dismal, right? Can expect to earn $26,000 per year. But an adult male whose high school GPA was 3, a little bit better there, or a lot better, can expect to earn $40,000 per year. Okay, so there's a definite correspondence there. I think this was valid data, but I don't know when it was measured. Definite correspondence there, right, between how someone does in high school, right, and what their earnings there turn out to be. And this doesn't even include a college, correct? All right, so you see there the kind of the description of the problem, right? And the first thing that we're going to do there is, well, a couple of things. So we're going to take this one step at a time. Why is the relationship between y and x? Why do we know that that relationship is linear? And then second, what is then the slope of that linear relation? Once you have a linear relation, you must have a slope. So what is the slope? Okay, so those are the first two things we're first going to answer. I want y'all to work on that. Okay, and so I'm going to, so you understand what you're asked. Why is the relationship linear, and then what is the slope? But let me scroll back to the actual statement of the problem, because you need the statement of the problem there, right? Okay, all right, so I'm going to stop the recording here for a few minutes, so we're going to take a little bit of a break, but you can be working on this during the break, all right? And I will leave the a description there of the, I will leave the description of the problem, okay? All right, so we'll take kind of a problem break here. And then when we get ready, I'm going to ask someone to help me explain that, right? So everyone, to answer those questions, so everyone needs to be working on this, because I'm going to pick someone. I'm going to play a dirty trick on y'all and pick someone, all right, from the class, right? So everyone needs to be working on it, so you can be prepared to respond to me. Don't worry about if you're, if your response is, I'm not understanding this too well, that's fine, because we will then work through that, right? But be prepared to say something if I call on you. All right, so I'm going to pause the recording. Well, I'm going to try to pause the recording. Let me do it with my other mouse. All right, so were y'all able to come up with an answer there for why that this is a linear relation, without really, with just this verbal description here, why this is a linear relation? Let me ask someone. So I'm going to call someone. So don't be shy, don't be intimidated. All right, okay. We're going to talk it out, right? If we need to. And this is, remember, this is part of your class participation grade, right? But it's really easy to make a high class participation grade. All you have to do is just, really, give it a try here, right? So don't be shy. I'm going to ask Carla first. Carla, are you there? Can you hear me? You can chat if you need to. Let me switch back to my participant list there. I'm pretty sure I saw Carla come in. So is Carla there? Ooh, Carla's on the list here. Okay. Can you hear me, Carla?
I think Carla left.
Carla, one more chance there. All right, let me try. Let me ask another person. Daniel, are you there?
Yes, I am.
All right, Daniel. So, can you think of a reason why this is a linear? Why this is a linear relation?
It's a linear equation because the x and y's are related to each other, because to find the y we need to find the x.
That's certainly an important fact. Okay, so it is true that the x and the y are related to each other, right? Okay, because you know that's sort of very clearly described in the problem, Daniel. So we definitely have a relationship here, right? Or we definitely have a relation. But why do we know that this is a linear relation? So if we were to graph, we don't have enough information to do that yet. But if we were to make a graph of, this relation, right? So if we were to graph, these x and y related values that are in this relation, why do we know that that graph would come out to be a straight line? Why couldn't it not come out to be some other sort of curve? Right? So why isn't it, some parabola shaped curve or some other sort of curve, right, Daniel? Why do we know that it's going to come out to be a straight line? What's the language there in the problem that kind of tips us off to that? Go ahead.
Because of this, the slope, the rate of change on the slope.
Well, it doesn't mention rate of change or slope here in the verbal description of the problem. All right, but what does it say, Daniel, in the problem that's really crucial here? See where I'm pointing at to this part, right?
Yeah, as the high school GPA increases, their salary or their income will increase.
Right, but so when we make a graph, let me draw a really kind of crude graph here for us. If I can get my pen to work. So if we were making a graph of this is going to be, y. So that's going to be the salary, right? This is going to be x. So you're right. As x increases, right, as we're going left to right on the x-axis, so as the GPA is increasing, right? It's right. The salary is increasing. That's true. So, but how do you know it, Daniel? It doesn't look like this. See, if I drew the graph like this, the salary would be increasing, right? As the x gets larger, right? So, but that's not a straight line. So what kind of tips us off that when we make this graph, we're going to get a straight line instead of a curve like this one? So you do have a curve that's increasing though. So this one's increasing from left to right, right? Okay. So you do have a picture like this, but why is it a curve? Why is it a straight line and not a curve? Go ahead.
The amount it will increase, it will be the same amount. It doesn't change. For example, if we increase, and for example, if we say the x is 3 and the y is 4, and if the linear the linear is gonna increase in the same amount of rate.
That's right. There's where that's the key, Daniel. Okay, that's correct. Because notice what it tells us here is that the earnings is increasing at a steady rate. Okay, the earning is increasing at a steady rate. All right, as the high school GPA increases. See, that's not the case in this picture, right? In this picture that I drew, when x is increasing at first, the salary is not going up much, right? But when you get over here a little bit further to the right, as x increases, the y really starts going up fast. So the salary would be going up much faster, right? That's not a steady rate of increase. But in this problem, it tells us, oh, the y is increasing steadily as x increases, okay? So you cannot have a curve like this one. Instead, you must have got to have a straight line like this, right? But y is increasing at a steady rate when x increases. So there you got it. That's why we know this is that's why we know that this is a straight line. So we don't have a graph of this, right? But when we do make a graph, it's going to turn out to be a straight line. So that being the case, let's see now if we can calculate the slope, right? So all lines have slope. So this line that's relating y and x here, no matter what it ends up looking like, I don't know what it ends up looking like, right? But this line is going to end up having a slope, right? Okay, so we should be able to calculate the slope. All right, so that's the next problem. There is what is the slope? So Daniel, before I let you go here, I'm not going to ask you to do the calculation, but Daniel, what pieces of information do you need to know to calculate slope?
The change in X and Y.
The change in X and Y, right? Because remember, just to write that
slope
down
is,
again. Remember,
right
the
over here.
slope was the formula for that is the change in Y divided by the change in X, right? Remember, in calculus, we use this Greek letter delta to represent change if we don't want to write out the word. So, so slope is change in Y divided by change in X. But in order to calculate change in Y, or in order to calculate change in X, what pieces of information do you need about your line? What particular piece of information do you need to know about the line, Daniel?
The
Remember?
point. The
Point, right.
the
You need
the
some
line
points, correct? And how many points do you need?
minimum 2, like 2 points.
2 points, right. So to actually use this slope formula, we need to know 2 points that are on this line. Well, Daniel, do we have enough information to do that? To write down 2 points? Can you tell me 2 points that are on this line?
Yeah, we have 1 point with 1 point GPA, we have 26,000.
Yeah,
And the
there's
other
1
point
point that's on the line. And what's the next one?
and 3 point GPA is going to be 40,000.
There you go. So we know 2 points on the line, right? So that means now we can calculate the slope. Remember, the way you compute change in Y is Y sub 2 minus Y sub 1, right? That is Y coordinates of 2 different points on the line divided by X sub 2 minus X sub 1, the X coordinates of those same 2 points on the line. All right, so you guys calculate the slope for me. There's the formula, right? Okay, so actually compute the slope and tell me what that number is. That shall take you about 30 seconds to do that, right? Okay, so you can come out with a really nice, easy calculation here. All right, so compute the slope for me. Don't say it because I'm going to ask someone. All right, or did you have a question, Saad?
I actually already
Somebody
that.
already wrote it down for me there. Who is that? Is that Saad? Oh, okay. All right. So Saad, I'll ask you. Let me cover that up so everyone can compute that. But I'll ask you in a minute, Saad, what it is. All right. So you guys take a few seconds here to compute that for me, and then we can compare your answer to what Saad's going to tell us here. So I will just sit here patiently while you guys are doing that. Okay, so really that's a pretty fast calculation, right? Because you can almost do that calculation in your head. Saad, what did you get? What did you get there for me?
I got 7,000.
Perfect. Yeah, right. That's just going to be 40,000 minus 26,000 over 3 minus 1. So that's 14,000 divided by 2, right? 40,000 minus 26,000 is 14,000. 3 minus 1 is 2, right? So you get 14,000 over 2, which is 7,000, right? So there is there is the slope. And usually now, we denote the slope by m, correct, right? So there's the slope, 7,000. Once you've got the slope, then you are really you know really everything about your line. Okay, so lines are really crucially related to the notion of slope. Okay, and so once you know the slope, you're really sort of on your way with lines. So can you write down for me quickly now the equation? So we just started with a verbal description of this line, but now we can actually write down the formula for this line. And then once we've got the formula for the line, I guess we could graph it too, right? So can y'all write down for me that equation, the equation for this line? So I need y equals, and what is the formula for this line? Okay, What's the form? Do I need to scroll back up, or do y'all remember enough of that information? What is the formula for this a line, right? The slope is the slope there was 7,000. There's the slope, and then what is the formula for that line once you know that slope? So take a minute or so to write that down, and I'm going to ask someone. Don't tell me before I ask, though. Okay, all right. I'm going to ask someone just to share that with me.
So what are we writing? The formula?
The
of
formula,
slope?
yeah, the formula for the line. Y equals, and then
yeah,
what's
yeah,
that formula for?
right.
What's the
Gotcha.
formula for that line? So this is the information. I scrolled up because this is the information that you have, right? There's the slope, 7,000. Remember, we knew these 2 points on the line, right? Daniel told us those 2 points on the line. That's really the information that we have about the line. So can we use that to write down the formula for the line? So if you can only get started on it, that's great, okay, right? Do as much as you can. Try to recall as much as you can about how to do this, even if you cannot do it completely. That process of trying to remember, even if you cannot fully remember, that process is what builds neural connections in your brain. It's kind of like using your muscles at the gym. So when you're building those neural connections in the brain, you're making your brain stronger. When you make your brain stronger, that's called getting smarter. So that's what you'll be doing here. Even if you cannot fully remember how to do it, just the process of trying to remember is what's making you smarter. All right, let's see if we can write this down. What's that equation based on the information that we have? So I'm going to ask someone again, and again, just tell me what you know. All right, and we'll talk through it if we have to. Kevin, is Kevin there? Kevin Arbasto? I may have several Kevins. Kevin, are you there?
I'm here, sir, but I'm kind of lost about it.
Okay, well, that's great because we're gonna find you. All right. Okay. So remember, Kevin, you know the slope, right, was 7,000, and a couple of points there on the line, and that's all the information that you need for writing down the equation for the line. Okay, because you can use what is known as point slope form for the equation of the line. Do you recall that from those, we were going through those key features of lines? You can use point slope form. So this is in your notes from this set of notes somewhere way up there. This is the point slope form.
Oh, okay. Yeah, I see it
Kevin.
here in my notes.
Yeah, that's the point slope form. And all you have to do is fill in the numbers in this equation. The X and the Y are the variables in the equation, so you don't fill those in. It's the M, the X1, and the Y1. That's what you have to fill in, okay? And the M, of course, is the what?
The slope, 7,000?
7,000, right? So you have 7,000 here, X minus, and the X1, Y1 is some point on the line. That's the coordinates for some point on the line. Any point on the line will work. All right. So that's a great thing about straight lines, by the way. Any point on that line will work. So so do you know some points on the line?
Yeah. Was it?
Yeah.
Wait.
Right. So you just fill those coordinates in. So whichever point you want to use there, Kevin, let's just fill it in. So what would go in right here for X1?
X1, like 1 or
1. Yeah, like 1. Yeah, exactly. Plus, and then just put the Y coordinate for the same point, which is what's the Y coordinate for that point that had X coordinate 1?
26,000.
There you go. Yeah, there you have it. So that's all there is to it. See how easy that is?
Okay.
Yeah. And there is a formula. There are other ways of writing this formula, but there it is. There's a formula for this this relation between x and y. And now you can use that formula for doing, whatever you want to do with this line, right? Okay. So perfect. Oh gosh, I ran out of questions. How did that happen? All right. So let me tell you one more thing about this problem, though. Let me remind you about the interpretation of the slope. So the slope here is going to tell us again that is the amount that y changes when x increases by 1. But remember, y is the average annual salary, right? So we would say here the average annual salary increases because the slope is positive, increases by 7,000, right, when the high school GPA increases by 1. Or you could say the average annual earnings increase by 7,000 per high school GPA point. Okay. All right. So there's kind of the contextual way of interpreting slope. Okay. All right. So well, we got 15 minutes left. So let's see how far we can make it into our next set of notes. So y'all did really nicely on that one. All right. So let's switch here to our next notes. So now we've talked about relations in general, right? Okay. And some of our relations are linear relations, but not all of them are linear relations, right? Some of them are a little bit more complicated relations. So and that's going to be kind of an issue for us in calculus. Is relations can be very complicated between quantities. So sometimes when you graph relations between quantities, you're going to get kind of complicated graphs, all right, not straight lines. So here's an example of a relation between two quantities, x and y. This is obviously not a linear relation, right? Because you've got lots of square exponents in this equation. Remember, you don't get that in a linear relation, right? So, but when you graph this relation, you get this really nice, pretty curve, right? And notice this curve has this nice loop in it, all right? So this is a perfectly good relation, okay, right? And it's got a really nice, pretty curve here. But the fact that this curve has a loop in it, all right, that's going to sometimes create issues for us with for us in calculus, all right? So now that doesn't mean that we're going to, in calculus, ignore relations with complicated curves like this one, all right? But to get started here, we're going to kind of focus our attention on relations where the curves are not quite as funky as this one, all right? And so we're going to restrict our attention here at the beginning to a type of a relation that's called a function, all right? So I know you've heard a function a lot, all right? And so that just refers to a particular, let me see if I can get my windows out of the way so we can see the definition a little bit better here on the screen. So a function is a particular type of relation, all right? And that's a relation where, remember, a relation is a set of ordered pairs, right? Okay. So in a function, you only have, in a function, if you look at all the ordered pairs in a function, each first coordinate is matched with exactly one second coordinate, all right? So each x coordinate is matched with one and only one second coordinate, all right? So that's the type of relation that we're going to restrict our attention to here for a moment, for a little while in the class. And again, that type of relation is called a function. Let me show you that this relation that has a loop in it here. So it's a nice, pretty graph, and it may be a very useful relation, But again, we're going to try to ignore that initially for the class. And let me show you why this relation is not a function. Because again, keep in mind, right, that you know, when all of these points on this graph are just ordered pairs. Well, if you look at, for instance, there are other examples of this, but if you look at these two ordered pairs, right, what do you notice that are part of this relation? Notice that they both have the same x coordinate, right? So the x coordinate for both of these points is 2. The y coordinate, I can't tell it exactly, but it looks like the first one there looks like that's about, wow, I don't know what that is. Maybe minus 0.2 or something. And it looks like this one is something like maybe minus 1.9. I'm just guessing what the coordinates, what the second coordinates for these 2 points are. Okay, I'm just trying to eyeball it. But look, see, that cannot be a function because notice this x coordinate matches different y coordinates in this relation. In a function, that will not happen. Each x coordinate will match just one y coordinate. So you won't have the same x coordinate matching 2 different y coordinates. And when you put that restriction on a relation, when you make a graph of the relation, you therefore will not get loops like this one in the graph. And that is going to be an advantage to us in calculus, in our early study of calculus, to not have graphs with the kind of these funky loops in them. Okay, so we're going to pretend here for a while that all of our relations that we're dealing with are just going to be functions. So they're going to have this special property again that every x coordinate is going to get matched with one and only one y coordinate. All right. Remember back at the beginning of the class, right at the beginning of the class when we defined relations, I showed you these 2 relations, just sets of ordered pairs, right? And I said there's kind of a difference in these 2 relations, but I didn't go into what the difference was. Well, the difference is actually that one of these relations is a function and one of them is not. Okay. They're both perfectly good relations, but the second one is a function. B counts as a function, but A does not. So why does A not count as a function? So what about this relation keeps it from being a function? Someone want to tell me that? So why is A not matching our definition of function?
I can't see it, but
Someone want to help me with that? What?
There's multiple values for certain x values.
Colin, you said it perfectly right. There are multiple y values for certain x values, right? For example, Colin, what?
I can't see it, but I think it was 1 and minus 1.
Is other people seeing it? Or is it just, or am I doing something wrong? Yeah, these 2 right here, okay, for instance, that same x coordinate minus 1, right, has different y coordinates there, right? This here in this ordered pair, minus 1 is matched with minus 1, but in this pair, minus 1 is matched with positive 1. Okay, so you cannot have that in a function. So it's a good relation because it's just a set of ordered pairs, but does not count as a function. What?
Professor? Are you showing us a different graph? Because we're still looking at the 3 question from the previous problem.
Yeah, I'm looking. Yeah, I have. I've scrolled here. So have I lost y'all there somewhere? Can y'all see this?
Yeah,
what?
it's the screen is frozen, not the previous problem.
Oh, the screen is frozen. Okay, let me pause the share here for a moment and then let me resume it and see if Did that help?
No, we're still at the last question.
All right, let me stop the share then, and then I'll restart it. So see if that helps. I am moving around, so is that any better?
Yes, we can see the new one now.
Oh, okay. All right. So sorry about that. All right. So you guys try to do that again. If things start messing up, then let me know quickly so we can fix it. Right. So -1 is matched with two different, that same x coordinate -1 is matched with two different y coordinates, right? So you cannot have that in a function. Actually, the same thing happens for 2, right? 2 is matched with two different, a +2 x coordinates matched with two different y coordinates. So you cannot have that in a function. But notice that doesn't happen in relation B. If you just sort of go down the list there, you'll notice that, well, you don't even duplicate any of your x coordinates, right? So you cannot have the same x coordinate matched with two different y coordinates here in relation B. So relation B counts as a function, but relation A does not. Let's quickly here, we have just enough time, so let's go through and I just want you to tell me here, y'all can all answer me at once, which of these is going to be a function and which is not. All right, so they're all relations, okay, but some are functions and some aren't. So what about A? Is that a function or not a function?
Not a function.
It's a function.
It's a function.
Yeah, that is a function. I'm trying to fool you here in all of these questions, by the way, because notice in this case, I've got the x coordinate and the y coordinate are always the same, but that's okay. That still counts as a function because you do not duplicate x coordinates with different y coordinates, right? Every time you have an x coordinate, a different x coordinate, you get a different y coordinate, right? Okay. All right. So yes, A does count as a function. What about B?
Not a function.
Yeah, I caught you there, right? Is that Andres?
Yeah.
Okay. Yeah, that is a function. All right. Yeah, I was trying to fool you in all of these. This really is a function. It's okay if you repeat the y coordinate. What you don't want to do is repeat x coordinates. All right. You don't want to repeat x coordinates. That's what doesn't happen in a. You don't want to repeat x coordinates with different y coordinates. All right. So this one really counts as a function, even though the y coordinate's always the same. What about C?
No.
Not a function.
Yeah, and what messes that up is right here, right? Okay, so we repeated the x coordinate, and that really shouldn't happen in a function. All right, you repeated x coordinates with different y coordinates, so this one is not a function. And then what about D there?
No.
Yeah, it is a function.
Yeah, again, it's a trick question. The answer there really is yes, okay? Notice I repeated the x, right? But it still has the same y value, okay? Still has the same y value. So this one really does count as a function, all right? Although the x coordinate is repeated, it's repeated with the same y coordinate, okay? So you don't want this case to occur, the x repeated with different y's, but if you repeat the x with the same y, that's really okay, all right? That's kind of would be an unusual situation to occur, but technically that counts as a relation. So it turns out when you make the graph of a function, as I mentioned, you're not going to have loops in the graph, okay? And that's going to make our life a lot simpler in calculus. And there are other practical advantages to functions over relations as well, as other than just it simplifies the graphs, okay? There are other reasons why we prefer to deal with functions other than just relations in general. Okay. All right. So, well, we're going to talk a little bit more about functions and kind of the terminology that surrounds functions. And then And then we're ready to finally, we've sort of caught up with the terminology and review that we'll need for calculus. So once we finish talking about some of the terminology that surrounds functions, which is similar to the terminology around relations, but there's some specialized terminology, then we'll be finally ready to jump into new material instead of review material, calculus. Okay, so I'm gonna stop. I'm gonna stop there. We're out of time, so I have to stop there. So remember, your next homework is actually due on Saturday. I moved that back to Saturday. And you guys have a great weekend. All right. And I will see
Professor,
you,
you too have a good weekend.
God willing, on Tuesday.
Thank
I'm
you.
going
We'll see you
tomorrow
next
to get.
class.
I'm going tomorrow to get vaccinated.
Thanks,
So
Professor.
I will. So we'll see if I have a bad
Ooh,
reaction or something.
Congratulations.
So we'll see how that turns out. I'll let y'all know. Okay. So I'll see y'all Tuesday. All right.
Yeah. Bye, guys.
Bye.
You have a
Good
nice
day.
weekend.
Nice weekend, Professor.
Bye.